A good practical application of Faraday's law arises in the form of a very practical device, namely the AC or the alternating current generator, which is a pretty common device nowadays. So let's take a look at that. And an AC generator is essentially a rotating coil in a constant magnetic field. I've set things up. I've got a rectangular coil here, kind of wrapped around this. I'll assume that there's N turns in it, so it's wrapped N times around. And I've gimbaled it on here so that it's free to rotate about the Z-axis. In fact, I will force it to rotate, maybe have it hooked up to a motor or something, at the angular velocity omega, or the angular frequency omega. And I'll have it in a magnetic field, B naught, that's nice and uniform, but is pointing in the Z direction. And we'll consider that from the standpoint of Faraday's law. If I look down from the top, I see the rotation axis here, coming right out at me. The coil is rotating in this sense, the way I've got it drawn over here. I know that any area, an enclosed area, the area enclosed by this coil is planar, and so it has an area vector associated with it, which I have to specify the direction with the normal. And so I'm going to specify the normal of the coil when I catch it in this fashion here, in this direction. And B is in the positive X direction. And you can see that the way I've got it drawn here, that the angle that the area vector, or the normal to the area, makes with the x-axis is theta, and also the angle that this coil makes with the magnetic field is theta. And of course, as this rotates, well, theta gets larger, so theta, in fact, is a function of time. The way I'll set it up is to catch it. I start my clock when in hat, the normal is pointing in the positive x direction and rotates around in that direction. Well, as Faraday's law, we have to compute the magnetic flux cutting the coil, or one of the coils, in this multi-turned coil. And remember the magnetic flux, if the magnetic field is constant and the area is a constant vector, then this becomes very simple. B dot dA is just the magnitude of B, the magnitude of the area times the cosine of theta. The area is the area of the coil here on this face. If this were the length and this were the height, then it'd be length times height. The angle theta here is the angle between the magnetic field vector and the area vector. That's just the way I've aligned it here. The magnetic field is in this direction. The normal, or the area vector, is this direction, so theta is just the same. Theta is up here. I know it's rotating with constant angular velocity, and if you remember rotational kinematics, for uniform angular acceleration, we have this equation. In our case, alpha, the angular acceleration, is 0, and so we get, in general, theta is equal to theta naught plus omega t. But if I start it so that at time t equal to 0, theta is equal to 0, then that forces this constant term out. And so if we do that, it really just depends on when we decide to start our clock to measure time. That angle is equal to omega times t. Just to recall a little bit, the angular velocity, or the angular frequency, is related to the usual frequency. Remember, usual frequency is 1 over the period, and omega is 2 pi times that frequency. So, to get the magnetic flux, it's changing, but not because B is changing, not because the size of the area closed by the loop is changing. B and A are constant. These magnitudes are constant. The way that you get the flux changing here is because the angle it makes changes with time. So when we put omega T into there. So by Faraday's law, in the form that I've been using it, the induced EMF induced in the coil is equal to minus the number of turns times the time rate of change of the magnetic flux through one of the turns of the one of the loops of the coil. And we just plug in our expression from above with BA cosine theta with theta equal omega T. B and A are constant. It's a nice uniform field, constant magnetic field. And A is of course the total area of the coil. It doesn't change, so we pulled both of those outside. And then I'm just left with the derivative of cosine omega T, which is minus sine omega T, and so the minus and the minus will cancel, and I'll just get omega sine omega T for that derivative with the minus signs going away. Pretty clearly for any specific coil that I'm rotating in this field, the number of turns doesn't change over these cycles. The magnetic field magnitude doesn't change, the area doesn't change, and we're rotating at a constant rate. So all of this is a constant, and I can lump that into a single constant, which is this NBA omega. And I call that E naught. Again, it's constant. And so we get that the EMF in this rotating coil varies sinusoidally in that fashion. And there we've graphed it over at least a cycle or so, a little over a cycle. It's a sinusoidal function. Of course, it repeats indefinitely. It has a period 2 pi over omega. Sometimes it's positive voltage, so when it's above the curve, and sometimes it's below. And when it's positive, the EMF is in one direction, causing current to flow in one direction, in that induced current. And then once the EMF is negative, it causes current to flow in the opposite direction. So we have alternating current in this particular device. It oscillates between the maximum values. This E naught here for a specific generator is just a constant, and it oscillates between these the plus and minus E naught. And you might say, well, how do you utilize that? And it's fairly ingenious. Here's a coil. Of course, I've only got one wrap. This would have many wraps and then finally come out. I have a constant magnetic field. Maybe 2 different bar magnets coming in through here. And then I've got this on a rotary spit that I can turn. And here's a little handle that I can turn it so that it rotates. I turn it at constant rate omega. And so that's clear enough how you would do that. But how do you get and make use of the current that goes there? Well, you complete the circuit in the following way. Along this shaft, you run the end wire out here through these 2 split metal rings. And one of them comes in and it brushes it. You send it through a brush, the metal brush that brushes up against the edge of this one. So as this ring goes around, this thing rotates around here. The other one is down the center of the shaft, but it doesn't touch this inner ring. It comes out, and you have a similar brush up here that brushes up against this outer ring. And then you just connect to the outside, these 2, to whatever device you want to use it. When current's going one direction, it's going to flow through here, around, back down. When it goes the other direction, it's going to go the other way, around and up and back around. And so you get alternating current that's coming to this resistor, if you will, or I've got a light bulb here that can use that alternating voltage, the alternating EMF that's generated by this device, and the alternating current. And you just make sure the frequency is going so fast that this light bulb element never has a chance to really get dim. It's really flickering well, in the United States, the frequency F is of wall current is 60 hertz or 60 cycles per second. And that's the normal household AC that you have from your electric plug-ins for lamps and things in your house. And the voltage, the E naught, is typically in the United States is 120 volts. Now that changes from country to country. A lot of countries do, instead of 60 cycles per second, they use 50 cycles per second. And instead of their household voltage being 120 volts peak-to-peak maximum, or 120 maximum magnitude, they use 240. But you see a number of different conventions that different countries have used and do use still. Well, that device up here, pretty obviously, we don't have people cranking a handle rotating this 60 times per second. But we do other things. We do hydroelectric, so you put a water turbine over here, and the water falls on it and makes it spin, and you have it geared down so that it rotates at a constant speed. Or that would be hydroelectric generation, or you generate it with natural gas turbines. That's the more common way in Oklahoma to do. They use natural gas, burn it, and that runs a turbine that does the same thing. It runs an engine that basically turns this. Or you have you get your AC a gasoline-powered generator as an emergency backup for whatever time you needed electrical power. So you get a little Honda electrical generator, and it runs on the same thing. There they use a gasoline-powered motor to turn this at a constant rate. So there's different ways of doing it, but the end result is that you generate alternating current. And that's really the most easy current to deal with. Easy to generate and very cheap to generate. Well, that device, this AC generator, is usually given this symbol here. And really you should give two parameters. You should give the maximum E naught and the frequency, either F or the angular frequency. Most of the time, if it's coming out of the wall, they will assume that you know it's 120 volts, and they'll even assume that you know the frequency, which is 60 hertz. You would know that. So sometimes they leave these off entirely. In the lab, you can oftentimes adjust these, so they have AC voltage sources that you can change the amplitude, and you can also change the frequency. And so there you'd have to give both if you were generating it. But the ultimate effect is it uses Faraday's law to create alternating voltage, which causes the current to flow alternating around this through whatever device is using it. And it will do that 60 times per second, at least in the United States.